I consider an industrial furnace that is located on a very long column of refractory clay. So finally I have a column. Wait. The thermal conductivity of this material is 1 watt for each meter Kelvin, and with a cross section of 1 by 1 square meters. So this is a sort of square shape of a column. I consider in this case a two-dimensional 2D analysis. And during the standard working condition, we have that three surfaces of a column are maintained at 500 Kelvin. And one exposed, one surface cooled by convection, with a T infinite equal to 300 Kelvin and H equal to 10 watt square meter Kelvin. In this example, I have a suggestion of the mesh. Delta X equal to delta Y equal to 0.25 meters as mesh, suggested mesh. We have to evaluate the temperature field and the heat flux to the air. So we can do a sketch of this system. I have a square shape here. I have imposed temperature 500 Kelvin, and here I have convection. Okay? When you finish to copy, I start with the solution. Codice del fondo. Okay. Are you ready?
Professor, I'm sorry.
Yes.
Some of the words I can read. Could you please read?
Yes. I go back to the. Wait.
I'm sorry.
Okay. Okay, you can ask now.
Some of the words that you wrote, I can read. I'm sorry, because
you have
please read the sentences that you wrote.
Okay, yes, I can read it. Otherwise, remember that you have the text of exercises that you can download from Aula Web. Otherwise, I have a column or refractory clay with cross section 1 by 1 square meters, and so I consider a two-dimensional analysis. During the standard working condition, I have 3 surfaces at 500 Kelvin and 1 surface cooled by convection with this value of TH and T infinite and H. These values are delta X and delta Y as suggested mesh. I have to calculate the T of the field, the temperature field, and the heat flux from the hair to the hair, this one. Okay?
Yes, Professor. Thank you.
You're welcome. And I sketch again the system now with the mesh. So here I have TS equal to 500 Kelvin. Here I have TS equal to 500 Kelvin. Here I have TS equal to 500 Kelvin. Here I have T infinite and H. I have to do the mesh. Delta X and delta Y are equal, so I have to consider a square mesh. And in particular, this is colored mapped mesh, because it's a regular shape mesh. Okay, I name the different nodes. 1, 2, this is again 1, because I recognize an axis of symmetry. I have an axis of symmetry here. Okay. So this node is 3, 4, 3 again, 5, 6, 5 again, 7, 8, 7 again. So the unknown points are the nodes on this sketch, because the nodes on the boundary here, all the nodes on this line, the boundary here in light blue are known, because those points are at 500 Kelvin, okay? The unknown are only 1, 2, 1, 3, 4, 1, and so on. This is delta X, delta Y, sorry. This is delta X. I can now write for the interior nodes the equation obtained for the two-dimensional case with delta X equal to delta Y. You remember that if I consider two-dimensional case for delta X equal to delta Y, the temperature of one node is the average of the temperature of the lateral nodes. The temperature of a node 4, for example, is the average of the temperature of the node 2, the node 3, the node 3, and the node 6. Remembering this point, I can write for the nodes interior nodes the following equation that now I write. These are the equations for the interior nodes. Okay. Is clear for all of you this point?
Yes, Professor. It's
Okay. Now I have to analyze the two cases. Node 7, that is the same as node 7 on the other side, and node 8. So now I change the page and I write the energy balance for the node 7. Okay, for the node 7, I have to write a sort of energy balance considering all the contribution of 8 flux that arrive on the node 7. And in particular, I remember to you that I have node 7 was here, 7, 8, 7, when I have here, sorry, when I have here 500 and here 500, and here I have the T infinite H. So for the node 7, I have to write this steady state case, obviously, and I have delta y divided by 2. And from the bottom, okay. Now I write and then I will explain. All the equation is equal to 0. Substituting when you finish to copy, I explain. If you remember the boundary condition where the summation of all the heat transfer rate that arrive on my node, plus eventually if I have the generation by volume, okay, equal to 0. Okay, I have no generation in this case. This is for steady state. If you remember, I use I use the equation obtained from the equation to be solved for the interior nodes. For the boundary nodes, I have to write the energy balance. And the energy balance for steady state with no generation inside is nothing else the summation of all the heat transfer rate that arrive on my node equal to 0. In this case, for the node 7 here, okay, I have 4 contributions. One from the top, that was the node 5, that arrive on my node 7 by conduction. So this one is nothing else the Fourier equation, the Fourier law, considering the distance among the node 5 and the node 7, that is delta y, and delta x is the area related to my node 7. This one is a sort of area in the direction normal to the heat flux, and delta y is the distance between the node 5 and the node 7. This is the Fourier law. In the same way, for the side contribution from right and the contribution from left. The contribution from right arrive from the node 8 with delta x, the distance between the node 8 and the node 7. This one is the area associated to the small volume of my node 7. So I have to write the energy balance for this small volume, but as I mentioned, delta x in one direction, and this one is delta y divided by 2. Okay? So this one is nothing else, this area normal to the direction of this heat transfer rate. From the other side, from left, the heat transfer rate by conduction arrives from a point that is at 500 Kelvin minus T of node 7. Delta x is again the distance between the node at 500 and the node 7. And this one is nothing else, again, the area normal to the heat flux itself. And from the bottom, finally, I have convection in this case. So this is the Newton law, in which I have the transfer rate from the fluid to the node 7, and this is the area associated to this heat transfer rate. It's clear for all of you? So now here I have simply combined it together, all the contribution, and inserting the parameters, the values of the parameters, I can obtain this one, that is the equation for the node 7 to be inserted in the previous system of equation to be solved together to the other. It's clear? It's okay?
Yes, it's clear, perfect.
Okay. Now the same for the node 8. Now you are able to write the same type of energy balance and okay. The idea is absolutely the same of the previous case, so you can try by yourself to understand. This is again Fourier law, again Fourier law, this one is again Fourier law, and this one is Newton law. I can put together the different contributions and I obtain with numbers, I obtain this equation. Wait. Okay. Can I change my slide so I write the matrix?
Wait a minute, Professor.
Yes.
Okay, thank you. Thank you.
Okay, okay. Have you any questions? So finally, now again, a boring part that is to write okay, nothing so interesting, but I have to write the matrix of the coefficients, because now we have then, from a mathematical point of view, to solve this system of equations that is here represented zero. Okay, this is simply the coefficient, the vector of the unknown, that is the this is what I want to estimate, the vector of the temperatures, and by using an inversion, a standard method for inversion of the matrix, I obtain the temperature that now I write to you. But here is simply to put in order the equations. Can I change? Wait, sì, ma non è che... Cosa? Yes, I wait. But the interesting part is the previous one, when I have to write from a physical point of view, when I have to write the energy balance for my node. Then this is a job made by computers. Now, and so finally T is equal to A, and the values are This is the first answer of my problem that asked to me to evaluate the temperature field. Now, weight flux for unit length of my column is 2h yes, I can write directly here 500 because it's better. I do now the sketch again of the system. Okay, I have the column was like that. So here I have T infinite H. This is at 500, and also this one is 500. I have now to estimate the transfer rate from this side. So I evaluate for unit length. For unit length means for unit height of my column. And here I have a 0.8, here I have a 0.7, here I have a 0.7. So this is the volume associated to the 0.7. This is the volume associated to the 0.8. This is the volume associated to the 0.7 again. I consider again an axis of symmetry. So again, I have the axis of symmetry here. So it's for this reason that here I have, here I have 2. Because I calculate this calculation in this bracket is for 1/2. Then I multiply by 2 to consider also the other half of my plate. And I have the first is this part. This one is the heat transfer rate by convection from this small portion. So is delta x divided by 2. Okay, this one is delta x divided by 2, this one. Okay, is Newton law for this portion. This one is the portion associated to the node 7. This one. And is thickness is length delta x. Finally, in which color I can use? Yellow. This one is finally half of this part of the node 8 as again delta x divided by 2. This is 1 by 2 because I consider the axis of symmetry. Is clear for all of you?
Yes, perfect.
Okay, fantastic. So if you finish to copy, we finish also with the examples, with exercises, and we go to the theory. We start convection. And I have to wait, and I have to open okay, can you see the slide now?
Yes.
Okay,
Yes.
va bene. And we start with a new chapter that is very long because it's the chapter associated to convection. And as you know, which is the important law, the basic law for convection is the Newton law. The Newton law is this one, is written in terms of watt for each for unit area, so power for unit, transfer rate for unit area, so it's flux. And it's a very simple law. Knowing the temperature of the surface and knowing the temperature of a fluid is simple to evaluate the flux. The problem is to estimate in a proper way the coefficient H. And the coefficient H is very difficult to be evaluated because it depends on a lot of parameters, a lot of operative condition. Depends on the thermophysical property of a fluid in terms of viscosity, thermal conductivity, density, specific capacity. Depends on the type of motion of a fluid, so its velocity, the geometry and the roughness of the surface on which the fluid flows. So it's very complicated. We have at the beginning in this chapter to start with a lot of definitions, definition and yes, observation of the physical phenomenon. First of all, we introduce the no-slip condition. If we observe a motion of a fluid on a surface, we can observe that at the surface, the fluid is motionless. That means I have zero velocity relative to the surface. The system that I will consider is always this one. Y is the axis normal to the plate, X is the axis of the parallel to the plate. So for Y equal to 0, the velocity of the fluid is always equal to 0. This is called no-slip condition. A consequence of this slip condition, in no-slip condition, is that I have the creation of a velocity profile. That means I imagine to have an undisturbed fluid that moves at u infinite before arriving on the plate. When the fluid arrives on the plate, at the surface, so for y equal to 0, is motionless, the velocity is equal to 0, and far to the surface, the velocity is still equal to u infinite. This creates a zone in which the velocity change from 0 to the undisturbed value, and this creates a sort of velocity profile. The shape is like this one. This zone is called boundary layer. Is the zone in which I have the change of the velocity from 0 to almost the undisturbed velocity. Wait, I have to change. Okay, wait. A consequence, interesting consequence, but we will use to the fact that I have a no-slip condition is that if the fluid is motionless at the surface, so for y equal to 0, the fluid is motionless, I can imagine to consider on this fluid conduction. If you remember, the difference between convection and conduction is that for convection the fluid is in motion, but I can have conduction also in fluids, but fluids not in motion, motionless. On the thin layer near to the wall for which the fluid is motionless, for the no-slip condition, I can consider conduction. So I can write that the heat flux exchanged by convection is equal to the heat flux exchanged by conduction if I apply the Fourier law at the wall, so for y equal to 0. This one is the Fourier law, but for y equal to 0, so only on the plate. If I substitute to this heat flux for convection the Newton law written in terms of heat flux, so watt for square meter, I can obtain an expression for the convection coefficient. So here I substitute in this convection the Newton law, and then I solve this equation for H. And finally, I obtain that the convective coefficient can be written as, yes, the Newton law, the Fourier law at the numerator divided by the delta T, expressed in watt square meter Kelvin. Another step, because at this point is nothing interesting, but if you remember, which is the number, the dimensionless number to represent the convective coefficient H, is the Nusselt number. Frequently in heat transfer we will use a dimensionless number to to find a manner to generalize the equations. Introducing the dimensionless number allows us to be able to write the law that controls the phenomenon in a more simple way, in a more generalized way. So if I want to associate to the H coefficient and dimensionless number, I introduce the Nusselt number. The Nusselt number is written as Nusselt equal to H coefficient, length L is the characteristic length of the phenomenon. This L, called, I repeat, characteristic length of a phenomenon, depends on the geometry that you are analyzing. In particular, if I am analyzing the motion of the fluid inside the pipe, I know that for this particular geometry and phenomenon, the characteristic length is the diameter of the pipe. But if I'm analyzing the fluid that flows on a flat plate, is not the diameter, obviously, the characteristic length of the phenomenon, but is the distance from the beginning of the plate. So this L is a length that depends on the phenomenon of the geometry that I'm analyzing. I go back to the Nusselt number. HL divided by K. K, thermal conductivity. Which is the difference between the Nusselt number and the Buoyancy number? Is defined in the same way, but as I introduced it to you when during the lesson of the Buoyancy number, the Nusselt number takes into account for H and K the fluid. Both H and K, thermal conductivity, are the property of the fluid. K is the property of a fluid, H is the convective coefficient. In the Buoyancy number, K is the solid thermal conductivity. Okay, if I remember that H in this Nusselt number can be written as previously, this one, I can simply simplify K with the denominator and divide all by L. In this case, I have a sort of a definition of a Newton number as the gradient of the temperature in the direction normal to the plate for the y equal to 0, so at the wall, divided by a reference, so-called gradient, calculated as the temperature difference between the surface and the fluid and disturbed fluid divided by the characteristic length of the phenomenon. This definition will be used by us later. Now is not so clear the sense to you of this writing of a Newton number, but will be useful for us later. In this slide, we want to introduce the Newton number, and we introduce this strange manner to write it. But to consider from the physical point of view the meaning of the Newton number, we can consider this, this system that is a cavity. I have two walls, one at temperature T1 and one at the temperature T2, and a layer of fluid between the two surfaces that create a cavity. If the fluid is motionless, I have conduction, pure conduction. Newton number equal to 1. If the fluid starts moving, for example, caused by the buoyancy forces, I have the motion of the fluid and I introduce a convection, which is the sense of the Newton number. If I calculate the convection by means of its flux, so water divided by a square meter, by the Newton law, H by delta T is the difference between the two surfaces, and the conductive flux using the Fourier law, K, thermal conductivity of a fluid, delta T again between the two surfaces, L, that is the distance in this case of the two surfaces, doing the ratio between the two expression, I obtain exactly the Newton number. That means the Newton number for this geometry expresses the enhancement of the transfer rate of its flux in this cavity due to the motion of the fluid, due to the convection. Newton is equal to 1 for pure conduction. If I increase the motion of the fluid, increase the convection, its flux, Newton become bigger than 1. See?
I have a question. You say that L is the characteristic length of the phenomenon.
Yes.
If we have a wall and, for example, air,
yes.
We are considering y equal to 0, so L is equal to 0.
No.
It's not the distance.
No, the distance is x.
Okay, so L is on the x-axis.
L is depending. We will study it, but if I have to evaluate, for example, the Newton number, I have local Newton number, that means characteristic length is x, the distance from the beginning of the plate. I can consider also the Newton average value for a portion of plate, that is Newton L, with L is the total distance from the beginning to that point. The same for the Reynolds number, but okay, I will clarify this point later. In such cases, for this type of geometry, that is a flat plate with fluid that flows on it, the characteristic length of the phenomenon is, you can consider now at this moment, the distance from the beginning of the plate, the x point, the x coordinate. Okay? I can go?
Yes.
The layer.
Yes.
Okay, thank you. I said that we have two zones. A zone in which the velocity change from the zero value on the plate due to the no-slip condition to the zone in which I have undisturbed condition, U infinite. Okay, so I can define a zone that I call boundary layer for which I have this change of velocity. In this particular sketch, I have the developing of a boundary layer in laminar flow, transition region, and turbulent boundary layer. Because later in slides, we will define which is the laminar flow, which is the turbulent flow, and which is the transition. At the beginning, I have laminar flow, that is ordered flow without eddies, and I have a developing of this type of profile. Then I have a transition zone in which the Prandtl number increase, and I have the change between the laminar zone, the laminar regime, and the turbulent one. The turbulent one is characterized by eddies. Eddies means in Italian vortici. So you can see here that I have the velocity arrow that have not only the component parallel to the plate, but a component normal to the plate. That means I have the creation of eddies. This is a turbulent boundary layer, the turbulent zone, in which the velocity profile is a bit different. But for both the laminar flow and the turbulent flow, I have a zone in which the velocity change from 0 to the undisturbed fluid, to the undisturbed velocity. How to quantify this thickness of a boundary layer? The boundary layer is a zone, this pink zone near to the plate. How to quantify this zone? I introduce the parameter thickness of a boundary layer. Wait, because PowerPoint does not respond. Okay, wait. Okay, I call delta. Delta is the thickness of a boundary layer. Outside this delta, for y bigger than delta, I consider that the velocity is unchanged, is u infinite. For y equal to 0, the velocity is equal to 0, I have no slip condition. How to quantify this delta thickness? Delta is defined as the distance y from the surface for which I consider the velocity equal to 0.9999 of the undisturbed velocity. Obviously, is a theoretical line, okay? It's a manner to introduce this thickness. So here in red, you have the definition of the two boundary layers of the boundary conditions of the boundary layers. Lower part, no slip condition, velocity equal to 0, y equal to delta, 0.99 of a u infinite. Another definition, I introduce another parameter that it's important. Keep in mind that when an engineer study thermal problem associated to convection, an aspect that is always coupled with convection problem from a thermal point of view is the fluidodynamic point of view. So for example, if I have to size an heat exchanger from the thermal point of view to, for example, obtain a good performance from the four-way transfer rate of my heat exchanger, I have also to analyze the heat exchanger from the point of view of a pressure drop. Because if my heat exchanger is fantastic from the thermal point of view, but want a pump of a lot of kilowatt because the pressure drop are very high, is not a good heat exchanger. So together with the thermal problem, I have to consider the fluidodynamic problem, that is the problem of a pressure drop finally. Which is the parameter, the basic parameter to evaluate the pressure drop is the shear stress. That is the friction force of a fluid that flows on a plate. It's called shear stress and is surface stress in particular. Tau S means at the surface. Here we write the expression for the surface shear stress for the Newtonian fluids. Newtonian fluids are fluids for which the shear stress is written in this way. If one asks to you which is the definition of a Newtonian fluid, you can answer the Newtonian fluids are the fluid for which the surface shear stress is proportional to the velocity gradient. Okay, and okay, depends. Finally, the surface shear stress depends on the viscosity, the dynamic viscosity, that is a thermophysical property of a fluid, multiplied by the gradient of the velocity. Velocity u component. U component is the component parallel to the plate in the y direction at the wall, so for y equal to 0. The sentence here at the bottom of part of the slide, remember us that the viscosity of liquids decrease with temperature, the viscosities of gases increase with temperature. This is, I know that this is a bit boring part because it's definition, but we introduce the alphabet to speak after about this topic. And another manner to write the surface shear stress, this one is for Newtonian fluid written in terms of a gradient of a velocity in the y direction for y equal to 0. I can also introduce a coefficient that is called CF, friction coefficient, that is a dimensionless number, dimensionless parameter, that allow us to express the surface shear stress using the undisturbed velocity of the flow, u infinite. I know that the fluid arrives at velocity u infinite near to the plate, and I want to express the surface shear stress by using this velocity, introducing this coefficient. Obviously, this coefficient change along the plate is not a constant value. CF is not a number, is not a thermophysical property of a fluid, is a parameter, is a dimensionless parameter that change along the plate. Tau S is the surface shear stress, is the force over the plate for unit area. If I want to estimate not the shear stress but the friction force in Newton, I have to multiply the surface shear stress by A, the area. So using the previous equation, I simply multiply by the area and I obtain my, my friction force. The most important part of this slide is the last sentence because it's the physical meaning. Okay, if you remember the shape of a boundary layer, increase x, I go back here. Increase x, x is the axis parallel to the plate. Increase x, I increase the thickness of a boundary layer delta. Okay, increasing x, I increase delta. If I increase delta, I decrease the gradient of the velocity in the y direction at the wall. Why? Okay, write well this sentence. Increasing delta, I decrease this gradient. Why I decrease this gradient? Because in the boundary layer, so in this pink layer, I have to go for all the point x from 0 to u infinite. If the thickness of this pink layer increase, means that I have more space to go from 0 to u infinite. That means that the average gradient and so also the gradient at the wall of the velocity decrease. Okay, it's clear this point. If this gradient decrease, also the shear stress decrease, because the shear stress is defined in this way, is proportional to this gradient. And if it decrease also tau s, the shear stress, and also CF. That means that if I move on my plate from the beginning, the friction decrease, the surface stress decrease, and so the friction force decrease along my motion over the plate. It's clear for all of you? Later we will be able to quantify this shape of CF and tau along the plate, because we will solve the problem for this case. But now, starting from the definition, we are yet able to analyze this physical behavior.
Sorry, I didn't understand why CF decreased.
Okay, decrease because if you understand this point is done. If I decrease this, I decrease also tau. If I decrease tau, tau is proportional also to CF. Okay. Okay, can I go on?
I'm sorry, Professor. I can't understand the last point that you, round U per round Y, what is why it is decreased? I can't understand.
Okay, I repeat, no problem. Okay, if I look at this sketch, if I increase X, moving from the beginning of a plate along the plate, the thickness of a boundary layer increase. The pink zone, that is the boundary layer, increase its thickness, and so also delta increase. Delta is the thickness of a boundary layer, okay? Which is the physical meaning of this point. That means that due to the fact that inside the boundary layer, I have to go from 0 velocity at the plate to 0.99 at the upper boundary of my boundary layer, isn't it? So, increasing delta, the thickness of a boundary layer, means that I have more space for this change of velocity from 0 to 0.99 u infinite. And so, the gradient of a velocity u in the y direction, that is this one, decrease because the same delta u must be obtained in more space. So this gradient decrease generally as an average, but also at the wall it decrease. Okay, it's more clear now?
Yes, Professor. Thank you.
Okay. Nothing, you are welcome. Okay, now wait, because I want to where I can stop. Okay. And we have a velocity boundary layer for the fluidodynamic point of view, and also a thermal boundary layer. Obviously, I have the creation of a thermal boundary layer only if the fluid that moves on the plate has a temperature that is different than the plate. But for me now, I analyze this case. The temperature of the plate is assumed Ts, and the temperature of the undisturbed fluid that arrive on the plate is T infinite, different values. And also in this case, I have the creation of a zone near to the plate in which the temperature change. The temperature change, and I have a creation of a sort of temperature profile. This is the shape here sketched in this slide. This is the shape of a temperature profile for the case for which Ts is lower than T infinite. If I have to consider the case with T infinite lower than Ts, the shape will be in this way, like this one. Wait, I have discovered a fantastic point that perhaps now I can try. Oh, wait. Because Mi hanno detto che funziona? No. Adesso ho fatto la mia, non va più il mouse. Ah, ok. Vabbè. No, they said to me that if I write on the... No? Wait, I have to test something, but it's not working. Vabbè, niente, I have to try to write on the slide another time. Fossa mi ha detto che si scrive, riesce a scrivere con la penna sulla slide, ma non ce la faccio. Ok, no problem. The shape of a temperature profile, if the T infinity is bigger than, is lower than TS, will be, now I move the point like that, okay? So, TS will be on the other side bigger than T infinite. But now look at this case. The gray zone near to the plate identify the thermal boundary layer in which the temperature change from TS to a reference value for delta T. As for the velocity boundary layer, I want to quantify this zone introducing the thickness of a thermal boundary layer, delta T. How to quantify this delta T? I say that the thickness delta T of my thermal boundary layer is the distance from the surface for which the temperature on this point minus Ts, the temperature of the surface, is equal to 0.99 of the maximum delta T, that is T infinite minus Ts. And this one is the definition of the thickness of a thermal boundary layer. Now, here at the bottom part in red, we have the two thermal boundary condition for my boundary layer zone. For y equal to 0, T is equal to Ts. For y equal to delta T, T minus Ts is 0.99 of T infinite minus Ts. Okay? Now, also here I have the last sentence that is important from the physical point of view. That is, also we can read also the sentences before. The thickness of a thermal boundary layer increase in the flow direction. So as previously for the velocity boundary layer, if I increase x, I increase also the thickness of a thermal boundary layer. The convection transfer rate anyway along the surface is directly related to the temperature gradient at that location. This sentence is not so clear for you at this point, but I go back to this one. Or also this one. The H coefficient, convective coefficient, is directly related to the gradient of the temperature at the wall. Bigger or lower is this temperature gradient, lower is the H coefficient, lower is convection. Now I go this last sentence that is very important for us. If I consider, obviously, Ts minus T infinite constant along the plate, so all the plate at Ts in all the points, the fluid as undisturbed fluid always far from the plate equal to T infinite. If I increase x, delta T increase. And this is absolutely clear for all of you. Increasing x, delta T, the thickness of a thermally boundary layer, increase. But if I increase delta, I decrease the gradient of the temperature in the y direction for y equal to 0. The same as for the previous case. I have to go from Ts to T infinite. Bigger is the thickness of this gray zone, that is the thermal boundary layer. bigger is the space along which I go from Ts to T infinite. So the gradient of the temperature in the y direction as an average is lower for increasing x, and also at the wall, so for y equal to 0, decrease if I move in the x direction. Is clear for all of you this point, up to this point? Okay, so remembering that I can write the heat flux by conduction at the wall. I go back to one of the previous slides in which due to no slip condition at the wall, the heat flux can be also written by using the Fourier law, because I can consider the fluid as motionless with conduction. So if this one decrease, also the heat flux decrease, and if this one decrease, also the H coefficient decrease. That is what I write in this sentence. If I increase x, delta T increase, but the gradient at the wall decrease, and so the heat flux and the H decrease along the plate. That means if I analyze the motion of a fluid over a plate, the convective coefficient H is not constant along the plate, but change along the plate. H change along the plate. Obviously, then I will consider to evaluate the transfer rate an average value for a portion of plate, but the H coefficient change continuously along the plate with X. It's clear?
Yes, perfect.
Okay. Now we introduce a free slide and then we stop for a break. We have introduced another dimensionless number, that is the Prandtl number. The Prandtl number is a number used to compare the behavior of a fluid from the fluidodynamic point of view and the behavior of a fluid from the thermal point of view. It contains thermophysical property of a fluid. The definition, if I have to calculate the Prandtl number, is cinematic viscosity divided by thermal diffusivity. So finally can be written in this way: dynamic viscosity, specific capacity, thermal conductivity. These are all thermophysical property of a fluid. So also the Prandtl number is a sort of thermophysical property of a fluid. In a table, you find for water the Prandtl number, for another fluid Prandtl number, because it depends on the fluid. And again, give us an information about the relationship between the behavior of a fluid from the fluidodynamic point of view and the behavior of a fluid from the thermal point of view. In particular, can be seen as the ratio between the diffusivity of momentum and the diffusivity of heat. So is the ratio between the ability of a fluid to diffuse motion and the ability of a fluid to diffuse heat in terms of perturbation of temperature field. This is the basic definition. For us, that we know now at this point the definition of thickness of a thermal boundary layer delta and thickness of a velocity boundary layer delta and thickness of a thermal boundary layer delta T, the Prandtl number is proportional to the ratio between delta and delta T. Now, for example, if I consider the Prandtl number as a ratio between delta and delta T, heat diffuse very quickly in, I consider two extreme cases, liquid metals and oils. For liquid metals, Prandtl number is very low. For oils, Prandtl number is very high. Here is written lower than 1, bigger than 1. But liquid metals, very low value of Prandtl number, oils, very big values of Prandtl number, which is the physical behavior. For liquid metals, I have that the heat diffuse very quickly with respect to momentum. That means that the diffusivity of heat here, that is at the denominator, is much bigger for liquid metal than the diffusivity of momentum. It's for this reason that the Prandtl number is less than 1. If I analyze the Prandtl number using the thickness of the two boundary layers, for liquid metals, I have that have a very low Prandtl number, means that the thickness of the velocity boundary layer is lower than the thickness of the thermal boundary layer. If I do a sketch of the two boundary layers, I have a slice, a very thin slice for the velocity boundary layer and a thick portion of space near to the plate that is the thermal boundary layer. The opposite behavior for the oil. For the oil, I have bigger diffusivity of momentum with respect to heat, so Prandtl number bigger than 1, and thickness of the velocity boundary layer much bigger than the thickness of the thermal boundary layer. Okay? These are two extreme behavior, liquid metals and oils. For the fluid that an engineer typically uses, that are water, gases, and refrigerant. Refrigerant for the chiller equipment, and then gases, including air and water. We can consider the Prandtl number more or less 1, 4. So more or less in the like a unit. That means that the thickness for the common fluid used by an engineer, the thickness of a thermal boundary layer is equal to the thickness of the velocity boundary layer. Is for the reason that for us typically we consider the same, the two boundary layer, because for the fluid that we use, Prandtl number is more or less 1/4, but it's the same. Laminar and turbulent flows. Laminar, okay, I have introduced at this point previously, but now we can read now that laminar flow is characterized by what? Tightly ordered motion. So the velocity component for the laminar flow is parallel to the plate. I have all the arrows that are in the same direction parallel to the plate. For turbulent flow, I have fluctuation, I have a creation of eddies, and I have a disordered motion. Obviously, the turbulent flow, so the creation of eddies, enhance the weight transfer, increase the mixing, and so enhance the weight transfer rate. The H coefficient by convection is bigger for turbulent flow with respect to the laminar flow. But enhancing the mixing, increasing the mixing, enhancing the weight transfer rate, I increase also the momentum transfer, and I increase also the losses by friction. Is for that I remember to you that when I speak about the behavior in heat transfer, I have to keep in mind behavior from the point of view of a pressure drop, because increasing the mixing, entering in the turbulent flow, I enhance the transfer rate, but I increase also pressure drop. Okay, obviously, transition between laminar to turbulent flow does not occur suddenly. I do not have up to a moment, up to the point, laminar and then suddenly turbulent flow. I have a transition zone, which depends on a lot of, again, of parameters, the geometry, the roughness. Roughness is rugosità. Italian, the velocity and so on. What is sketched here? At the beginning I have laminar zone, then I have a zone that is called a transition zone, in which I have a change step by step from laminar to turbulent flow, and finally fully developed flow, that is the turbulent flow. The number finally that allows us to quantify if a regime is laminar or turbulent is the Reynolds number. As you know, I define the Reynolds number as the ratio between the inertia forces and the viscous forces. If I have to calculate, is the undisturbed velocity multiplied by the characteristic length of the phenomenon divided by the kinematic viscosity. Or also I can introduce at the numerator the density and at the denominator the dynamic viscosity is the same. Obviously the units are no units because it's the dimensions of number. If I consider a small value of Reynolds number, means that the viscous forces are bigger than the inertia forces, and the viscous forces are large enough to suppress fluctuation, ordered the motion. For large value of a Reynolds number, the inertia forces are bigger than the viscous forces, and I have a creation of eddies and disordered motion. Conventionally, when I have to analyze the transition of the regime from laminar to turbulent flow, I can introduce the so-called critical Reynolds number. That is ideal, obviously, is not no physical sense in this critical Reynolds number, because you know that the transition is not a sudden sharp transition. But to simplify the analysis, we can introduce as a reference this ideal critical Reynolds number that control the transition between laminar flow and turbulent flow. Now we have to do a break. So see you at no, not noon is a manner to at 12. Okay. See you in a quarter of hour. At 12 we start again with a lesson. Okay. See you later.
Okay, Professor.
Okay, welcome again. We start again with the and I go back to the Okay, I share my screen again, this one, and I go here, no, wait, I go here, but now you can see no, wait. Okay. Okay, dimensional analysis, that is simply an application of a method that can be used in a lot of cases, and now applied to the convection case to obtain a link, a law, among the different dimensions and numbers. So the final aim for us will be to obtain, I go now at the end. We want to obtain finally that for the convective phenomenon we can write a correlation, an equation that link the Newtonian number that allow us finally to obtain the H coefficient that is our main problem in convection. So we can write the Newtonian number as a function of the other dimensions of number that are the Reynolds number, the Gratian number, and the Prandtl number. And use this approach. Okay, this method is consistent. We can read it directly at the beginning. We have to make a list of the physical parameters that control a physical phenomenon. Obviously, the phenomenon must be clear, more or less, to us. We have to know from the physical, empirical point of view, which are the parameter, the physical parameter that influence that phenomenon. In this case, for example, for convection, experimentally we can deduce, we can write that the flux depends on all the parameters here in bracket. Then I will analyze in details the parameters, but we list at the beginning the physical parameter that control a phenomenon. And we want, starting from the physical parameters, to identify some dimensions as groups. And in this case, we will identify 4 groups, Nusselt, Reynolds, Gratian, and Prandtl. And finally, depending on the different cases, the different geometries, different operative conditions, find correlations among the different dimensions as group. So in this dimensions analysis, first of all, we want to obtain which are the groups, the dimensions as group, that control the phenomenon, in particular convection for us. And we start by writing this one, that is the parameters that influence the flux in convection. And we list a lot of parameters that are n physical parameters. We can express each parameter by using units, fundamental units, fundamental dimension. If I identify n physical parameters, m fundamental dimension, for example, meter, Kelvin, second, and kilogram, n minus m give us the number of the dimensionless group that will be obtained. In our case, now I go to the next slide. In our case, we have 8n physical parameters that control the phenomenon of convection, 4 fundamental dimensions that are for us meter, second, Kelvin, and kilogram. That means that we'll be able to obtain 4-dimensionless group able to control the phenomenon, with which we will write correlations, different correlation depending on the case that we are analyzing. Which are the parameters that influence the convection? Okay. The heat flux depends on the undisturbed velocity of a fluid, obviously, that move inside my system. Depends on the characteristic length of a phenomenon, depends on the density, the specific capacity, the dynamic viscosity. Beta G, that is a parameter that introduce in the analysis the influence of the buoyancy forces. The next slide is focused on this parameter, but keep in mind that beta G is important when we speak about natural convection, which is the difference between natural convection and forced convection. In natural convection, the motion of a fluid is due to the buoyancy forces. The buoyancy forces are the forces created in gravitational field when I have zone of a fluid at different temperatures. If I have a zone of my fluid with higher temperature locally, if I have higher temperature, I have also lower density. You know that the density depends on the temperature. So higher temperature means lower density. In gravitational fields means that that zone of fluid with lower density rise up, and other zone that go down, with the creation of the convection movement. This type of behavior is called buoyancy forces. Beta G is a manner to quantify the buoyancy forces that are important when I speak about natural convection. Thermal conductivity, obviously, and delta T, the temperature difference between the wall, the solid wall, and the undisturbed fluid. I can rearrange this list of parameters in another way by introducing the heat capacity, C first, here called C first, but that is the product between the density and the specific capacity, and also introducing the kinematic viscosity instead of the dynamic one. At the end, I have this list of parameters. Now, this slide to explain better the meaning of the buoyancy force, the meaning of this beta coefficient that allow us to express the buoyancy forces. Okay, beta is defined as, this is a definition, nothing else, volume expansion coefficient. Volume expansion coefficient written here, -1 divided by the density by the first derivative of the density in temperature at constant pressure. This is the definition of a beta coefficient, the volume expansion coefficient. I can simplify, rearrange, approximate, the beta coefficient in this way. Convert the derivative with a ratio between differences. And in particular, I can write -1 divided by density, rho infinite minus rho divided by T infinite minus T, evaluated at constant pressure. For ideal gases, this expression become 1 over temperature in Kelvin. So when we consider when we consider natural convection of air, typically natural convection in a room, for example, is the air motion in a room, and air is approximated to an ideal gas, and so the beta coefficient will be evaluated simply by calculating 1 divided by the temperature expressed in Kelvin. Okay? By using this approximated formulation of the volume expansion coefficient beta, I can finally write the buoyancy force for unit volume. So this is the buoyancy forces are the force that act on a fluid to move it up in a gravitational field. Obviously, the buoyancy force depends on the density difference. Okay, I say to you that in a gravitational field, zone at different temperatures means zone at different density, means the motion of the fluid, because lower density the fluid rise up, higher density the fluid go down. The buoyancy forces for unit volume is nothing else G, but multiply the density difference. Using this approximated formulation for beta allow us to obtain an expression for the buoyancy forces that is beta G density temperature difference. So beta G is a manner to complete in the list of the parameter the influence of the buoyancy forces, because the density is yet contained in the dynamics viscosity, the cinematic viscosity, and the specific in the total its capacity. And delta T is yet here. We need to introduce beta G. Clear now from a physical point of view what is about buoyancy force? Ok, chi tace così. And now, okay, 8 physical parameters, 4 fundamental dimensions, 4 dimensionless group. We want to find these 4 dimensionless group. We have to define them and to then to be used in a correlation weight. And we can express the function written before as its flux f first, that is a generic function of the listed parameters, by using a power series. So that flux can be written, is nothing difficult. It's simply focus on the idea of this method. It's not a lesson of mathematics, it's a lesson of transfer. So focus on the idea of this method. The power of a dimension analysis. I can write the power series might flux using the listed selected physical parameter listed here. And the exponents are numerical constants. B, I, M, N, P, R are numbers. Here, the importance of the units. We know that in an equation, the first member must have the same units of the second member, obviously. So I need to know, obviously, the units of weight flux, U, L, Ni, because without knowing the units, I'm not able to apply this method. Okay, weight flux units is joule divided by second, that is watt square meter. And the same for the second. This is the velocity, U infinite units, meter second, meter is length, square meter divided by second is cinematic viscosity, its capacity joule cubic meter divided by Kelvin, beta G is meter divided by second to 2 Kelvin, K thermal conductivity is watt meter Kelvin, that means joule meter second Kelvin, and delta T Kelvin. Now I can write, I have 4 fundamental dimensions, meter, second, Kelvin, and kilogram. And I can write 4 equations to have the first member with the same dimension of the second. And I can write that, for example, 1 must be equal to Ri plus Ui. yes. Ri plus ui, because I want to obtain joule. 1 is equal to Ri plus ui. Then minus 1 is second. In the first member, second is here, is minus 1. Will be minus m on the second member, minus mi minus pi minus 2si, and finally minus ui. Okay, and so on for the other fundamentals dimensions. Okay. The method is more or less clear.
Yes, Professor.
Okay, thank you.
Yes, Professor.
Thank you to the student that always say to me, okay, Professor, because so I know if I can go on or not. So I have now a list of equations that link the different exponents, but I want to express some exponent as a function of the other. In particular, in this case, I select M, S, and R. And please switch off the microphone. And I want to write all the other coefficient exponents U, Z, P, N as a function of R, S, and M. And simply I obtain that U, for example, is equal to 1 minus R. Z is 1 plus S, and so on. Finally, you will understand why I do this. Because now...
I'm sorry.
Yes.
How can I understand that I should write the parameter depend on MI, SI, and RI? I mean, how can I understand that these
you select 3 parameters and then you write. It's the same for the other selection. You can also select U, S, and Z, for example. You have simply to write some parameter as a function of the other.
Oh, okay. Thank you. Thank you.
You're welcome. But we go on, and then we can better understand the approach. Why we want to finally to write U as a function of R, S, M, Z the same, P and M the same. We go back to the first power expansion. So we go back to the first power series. And now we know that U is elevated to M, and it's okay. L was to N. But now N for us is minus 1 plus M plus 3S. And I write it here. Ni was to P, but now for us P is R minus M minus 2S. And I write here. And so on for the others. Now, and this is the interesting point, I group together the parameters that are at the same exponent. So here I have M here, I have M also here, I have M here, and U infinite is to elevated to M. L is to M. Ni is to minus M, so it will be at the denominator. And I group together U infinite L divided by Ni. Bracket elevated to M. S, I analyze S. I have L that is elevated to minus is elevated to 3s. Then I have Ni that is to minus 2s. Then I have beta G that is 2s. And I have delta T that is 2s. So I will introduce in this bracket L23 beta G delta T divided by Ni to 2. All the bracket 2s. And finally for R, I have Ni here, then I have minus R for K and R for C. So the number will be in bracket Ni by C first divided by K all to R. And parameters with no exponent, but with, for example, -1 here is L, and I take out from the summation and is L here. Then I have here K, 1, again here K, and I have again delta T. Okay, so I know that its flux can be written as a ratio of parameters and then the summation with exponents. Can you recognize in the different brackets something? This is the Reynolds number. This is the Grashof number. This is the Prandtl number. And the first member can be rearranged, yes, because the flux, this one by convection, can be written as H by means of the Newton law, H by delta T. And I obtain H by delta T. I take this part on the first member, so it will be H by delta T by L divided by Ka, because I have put this part on the first member. Okay, divided by K delta T multiplied by L. You recognize something here is the Nusselt number. Finally, I have that the Nusselt number can be written as a function of a Reynolds number, Grashof number, and Prandtl number. It's not important that you write, reproduce all the steps from the point of view of writing this system of equation and writing. It's important that you understand the power of this method and the possibility to define the dimensions of this number and to obtain a link between the dimensions and number that will be useful for us when we have to write the correlations. Here, at this moment, we have obtained only that Nusselt number can be written as a function of Reynolds, Grashof, and Prandtl. But if you analyze, for example, in a laboratory, from the experimental point of view, a particular phenomenon, and you want to write a correlation, you already know that your correlation will be written in terms of Nusselt as a function of Reynolds, Grashof, and Prandtl. The coefficient will depend on the case you are analyzing, on the phenomenon, on geometry, on the operated condition. But the link between the different parameters, the different dimensions of number is this one, is always the same, obtained in this way. Which is the physical meaning of the Grashof number? The Grashof number is the ratio of buoyancy forces divided by the viscous forces, as is written in this way. The Grashof number is the number that we will use analyzing the natural convection. In forced convection, the Grashof number is not present. The Grashof number is present only in natural convection. Okay? Is clear for all of you?
Yes, Prof.
Yes,
Okay. Okay, fantastic. So now we have to start with the part a bit more complicated, because we have to obtain potential convection equation for the boundary layer. So I prefer to start this part next Wednesday. So for today, I stop here. Okay, it's okay. I know that we have half an hour, but starting now, no sense. So see you on Wednesday for this part. Okay.
Thank you, Professor.
Have a good lunch. See you next Wednesday. Bye bye.
Bye bye.
Your mouse, non va più.